Hey guys, welcome to your first video in Gen Chem. This is Unit 3, Atomic Structure and Periodic Properties, and today we're just going to be discussing atoms. So some things in this unit, or in this particular section, may be review for some of you, but please still write it down so that you are comfortable and you know exactly the language and vocab to use. So for this video, I'm going to move relatively fast just because a lot of it really is just basic level 1 factual information. So if you need to at any point in time, pause it, but do please listen in case I say anything that's exceptionally important. And I'll go ahead and get started. So atoms are the basic units of elements, and elements are substances that can't be broken down by chemical or physical means, meaning that they are the simplest organized substances on the planet. Now, beyond elements, you'll see that elements are made up of things. So sure, they can be broken down into something, but they can't be broken down into anything else that is considered to be matter. So elements consist of atoms, and every atom of a specific element has to have the exact same number of protons. Protons is the identity of the element. Okay, so the number of protons actually gives it its personality. And all elements are organized on the periodic table of elements, probably not surprising. Iron is one of them, and every iron in the entire universe should have 26 protons. As mentioned, the periodic table organizes all of the elements, and it is organized by atomic number. You'll learn very quickly where you find that number, but on this periodic table, it even says here on the key that it is in the top corner, and you'll notice that up here in the far top left corner, we have hydrogen with 1, helium with 2, lithium, beryllium, boron, etc. So essentially, you read the periodic table across a row, and then you go down to the next row and continue reading from there. An element name is usually abbreviated with its chemical symbol. A couple examples: oxygen is O, carbon is C, hydrogen is H. Oh, and we have another oxygen in here because it's HOCO week. All right, sorry. Usually we use the chemical symbol to abbreviate. It is either 1 or 2 letters. Sodium is an example of one that has 2 letters, but you'll notice that the first letter is capitalized, the second is lowercase. That is always the rule. The first letter is always capitalized. If there's only one letter, then you're done. If not, then the second letter is lowercase. A lot of times these letters represent the element's name, and it might be their actual name or it could be their original Greek or Latin name. Example is sodium. This is sodium, which, as you may know, S-O-D-I-U-M, there is not an N nor an A in that word. However, the original name for sodium was natrium, and so that is where the symbol came from originally, and then it was later renamed as sodium in the English language. Atoms are made up of smaller particles, but they themselves are the basic unit of all matter. This is kind of what an atom looks like, and the nucleus is way at the center, and then the orbits, which we call actual orbitals, which is different in chemistry, but the orbitals are just zones where we may find the electron. You'll notice that they are not the traditional, what we call the Bohr model, where it's just rings around a nucleus. And we'll actually do a lesson where we'll talk about why the Bohr model is incorrect and why we now know more about the atom. But the basic of it is that the nucleus is at the center and you have the electrons surrounding it. So as mentioned previously, the nucleus is a central part of the atom. The electrons are fast moving in the energy levels, but are also referred to as the electron cloud. They orbit the nucleus, but not in perfect rings. They stay in set distances from the nucleus, but they do move up and down. They move between energy levels, and the energy levels are not perfect rings or perfect disks, so we don't tend to visualize them that way anymore. This is actually slightly more accurate to what you would actually see if you could zoom into an atom. Now, this nucleus is far too large. The nucleus would be about 1,000 times smaller than that if this was the electron cloud. But you'll notice that there aren't really any organized orbits. They're just out there in different zones. Nucleus, as mentioned, is in the central part of the atom. It is made up of our protons and neutrons. Protons are positively charged. Neutrons have no charge. And so as a result, when you have a bunch of positive things with a bunch of no charge things, the nucleus becomes positively charged. So it itself has an overall positive charge that would be equivalent to however many protons there were in the nucleus. Now I'm going to give you a minute, and I would recommend you listen for a second and then just pause this when I tell you to and write down this chart. So The atom is made up of subatomic particles. Sub meaning below, so like submarine means below the water. And so these particles are what construct the atom itself. You've already been introduced to two of them, the protons and the neutrons. The last one is the electrons. Protons have a positive charge, neutrons have a neutral charge, electrons are negative. And then in this mass column, what I really just want you to get is that protons and neutrons both equal 1 atomic mass unit, or 1 unit, and electrons are almost nothing, extremely small. They are found in the energy levels, whereas both the protons and the neutrons are found in the nucleus. Now, we said that the electrons are placed at different energy levels, starting from the nucleus moving outward. The furthest ones that are in the furthest out energy level are referred to as the valence electrons. It is spelled like the curtain valence, but they are valence electrons. They are found in the outermost energy level, and if you think about it, when atoms come into contact with other atoms, that's when they're going to bond or react or do something, and so those are the electrons that are actually used for that. Valence electrons are used for bonding. They're also the ones that are gained and lost when forming ions, which we'll learn what that means soon. Now, this is actually a huge benchmark in the 2020 Colorado Academic Standards, and that is recognizing that the nucleus has all of the protons and neutrons. They all have mass units to them, so the nucleus is very heavy. However, with the electrons being extremely low mass, they do not make up a lot of mass. The electron cloud has a very, very, very low mass. All of the mass, pretty much, and we consider all of the mass to be in the nucleus. However, the nucleus is very densely packed, and so it is an extremely small area of the atom, and so it is lots of mass in a small volume, which means very dense. Okay. The electron cloud is very large, very spread out, and there's not a lot in it. And so this is a great representation of that. The nucleus, even though it is tiny, is where you find almost all of the mass of the atom, because all of the massive particles, the protons and neutrons, are there. When reading the periodic table, we can figure out a lot about an element. You'll get a periodic table in the next class, and you'll see that on that periodic table, slightly different from this one. In fact, you'll actually see on your worksheet that you see something slightly different than this one, your guided notes. But every periodic table has the same information. You have 4 things that must be in that box on the periodic table. You have the first one, which is the atomic number. That's the number of protons. We said that gives it its personality. So if the element is more reactive than others, you're going to see that it is because of the number of protons it has. So every carbon in the universe has 6 protons, period. So it has an atomic number of 6. If I were to add a proton, then it would become nitrogen. If I were to subtract a proton, it would become boron. So it's no longer the same element if the proton number changes. It really is the personality or the identity of the element itself. The other number that you find on here is the average atomic mass. Average atomic mass is the mass of all of the different types of that element that it can exist. So carbon can exist in a couple ways. We can find carbon as carbon 12, we can find carbon 13, we can find carbon 14. That means they all have 6 protons, every single one of them, but they might have different numbers of neutrons, which leads them to have slightly different masses. And when they do, we have to take that into account when calculating the global average atomic mass. It says it takes into account how abundant each type is. We'll do an activity with this so you'll get a chance to see it, but the basic idea there holds true, that it takes into account how abundant they are. Now, you can look at the average atomic mass, and if you were told that there are 3 different types or 3 different isotopes of carbon, and the mass is 12.011, well, you can probably assume which one's the most abundant. It's the one that is the closest to that value, which would be carbon 12. So they average themselves based on how abundant they actually are. Now, on your guided notes, it's slightly different, but the periodic table has those 2 numbers, the atomic number and the average atomic mass. And so what you can do is actually find out a lot of information just from that. Well, first of all, the atomic number is the number of protons, okay? Protons are positively charged. Electrons are negatively charged. And atoms traditionally should overall have a neutral charge. And so what that means is that traditionally, the number of protons and the number of electrons are going to be the same. Now, we'll see that there are cases where that's not the case, but you would have to have more information to know that. Otherwise, assume they're the same. So once you have the atomic number and you say that's how many protons, that's also how many electrons there are. Neutrons, a tiny bit, a little bit more complicated because it involves subtraction. But we already said that all of the mass of an atom exists in its nucleus. So if I take the mass of the nucleus and subtract the protons, I should have the neutrons. Because the nucleus is protons and neutrons. So if I eliminate the protons, I have the neutrons. Okay. Since all of the mass of the atom exists in the nucleus, we can assume that the average atomic mass, rounded 197, would be the actual mass of all the protons and the neutrons combined. Then you just subtract the protons and you have your neutrons. I want you now on your paper to complete this task with xenon, which is the element that is on your paper, and then please write a reflection. Heads up, those of you who listen this far, don't tell your friends. Well, tell your friends, don't tell your enemies. You may or may not have an open notes quiz that goes along with this, just to make sure we did our notes. Have a great day.